Great, thanks a lot, James, for the introduction. It's a pleasure to be invited back to another webinar after last year. Well, when MIDAS called me up this time, I told them, well, if, last year I presented part of the most current project I'm working on, but they said, no problem, you can present a past project. So to me, this is an oldie but a goodie, design of the new Fulton Road Bridge precast concrete arches. This is one of the first projects I worked on for Baker after they hired me after coming out of school, but not that it hasn't been all downhill from there by any means. It's been great, but this is still one of the my most favorite projects I worked on, so it's a pleasure to get to be able to talk about it again. On the presentation today, I'll begin with a background of the bridge, where the bridge type is located, talk just briefly about just the bridge type selection process, and then spend most of the presentation getting into the nitty-gritty of final design of the arches and modeling the bridge in MIDAS Civil. Depending on how much time we have towards the end, talk a little bit about construction, and then we'll have time to field any questions you might want to ask. And as has been the case in the past, any questions I don't get to today during the presentation, we'll respond to subsequently via email. So question will be answered if you have it. But in any case, the Fulton Road Bridge project, it's located in Cleveland, Ohio, just south of downtown, right here, and in a pretty culturally significant area of town. Zooming in a little more on the project location, the bridge crosses a valley in which the Cleveland Metro Park Zoo is located. It also crosses over two sets of active railroad tracks, one CSX and one Norfolk Southern. Looking at the bridge from the side, you can see that, particularly for visitors to the Cleveland Metro Park Zoo, it's a very visible structure. This is the part of the zoo where I think that this is where some of the tigers and bears are located over here. So everyone going over here to the zoo gets a really close-up view of this bridge, which I appreciated too during my 10 years at the Cleveland office for Baker before moving to Minnesota. Well, the original bridge located at the site was a cast-in-place open spandrel concrete deck arch. It was built in 1932, featured 6 210-foot arch spans, and had a lot of architectural detail, as you can see in this photo of the bridge shortly after it was opened to traffic. Unfortunately, the bridge was not maintained very well. That nice cantilever we in the previous photo you saw was removed, and the nice railing was replaced with just a chain link fence, which then allowed water to flow over the edge of the bridge and start deteriorating to deteriorate the spandrel columns. And by the time my supervisor, Jeff Broadwater, took me out to see the site during my job interview with Baker back in 2003, the original bridge was in a very advanced state of deterioration. I don't think I'd ever seen a bridge concrete structure quite that deteriorated. And in fact, some of the transverse diaphragms between the end piers were actually all the concrete, not just some of it, all the concrete was gone, and there was only a rebar cage just hanging in the air. And there were also, as a result of all this deterioration, as you can imagine, there was a fair amount of falling and crumbling concrete, so protective shelters were installed under the bridge for visitors to the zoo so that they didn't have any concrete all undone. Michael Baker International was engaged by Cuyahoga County Engineer's Office to perform preliminary and final design for a replacement structure. There was a lot of community engagement, talking with the community. There was a strong preference for an arch-like replacement structure. There had been another concrete arch crossing of the valley a little ways up that previously had been replaced with just a steel plate girder structure, and many people were still sorry that it had been done and not replaced with another arch. So strong preference for a arch structure, and as a result of during the preliminary design process, the selected alternative was a contemporary concrete arch bridge with contemporary appearance, so not trying to mimic a historic 1930s structure. So fewer spandrel columns along the length of each arch span, but still a actual concrete arch. Here's a kind of a diagram of the layout of the selected replacement structure. Still like the original structure, the replacement structure has 6 210-foot arch spans, concrete arch spans over the valley, while replacement structure has then precast concrete eye girder approaches on each end. It's a continuous bridge from end to end. One innovative thing about it is it has a prestressed concrete. It has a prestressed concrete eye girder superstructure which floats atop the 6 210-foot arch spans on bearings. So there's a single foot fixed point in the middle here, and then the superstructure is free to expand in either direction and sits on bearings on top of the spandrel columns and in piers. Other than this single fixed point in the center, there's a vertical crest curve on the bridge, so water drains off the structure using the bike lanes. So the idea is then to keep all rainwater and any salt-infested water from removing snow off of the concrete of the bridge. Well, here's the cross-section of the bridge. Like the original structure, there are 4 arch ribs. Difference here, though, is these arch ribs and the replacement structure are precast concrete rather than cast in place. The spandrel frames, just due to the vertical curve on the bridge, all of the spandrel columns they're all slightly different heights. So the thought there was that precasting would not be an efficient means of constructing the spandrel columns and spandrel frames because every one was a little different. So they're cast in place over the arch ribs, and then the superstructure is a standard for Ohio precast concrete eye girder I-beam superstructure supporting 4 traffic lanes, 2 bike lanes, and wide sidewalks on either side. So let's look at a typical arch span. So each arch rib and each span is made out of 3 precast segments with their 2 types of segments, the arch end segment and then the arch crown segment, which are joined together with cast-in-place closure pores between the end segments and the end piers and the end segment and the crown segment. The precast segments have little pedestals here for the cast-in-place spandrel columns are cast on top of. Again, each arch span is 210 feet. So now let's get into a bit of the final design of the structure. I'll talk about the post-tension requirements for the arches, how to determine what the effective length should be for slenderness effects, moment magnification, and then I'll talk some about superstructure-substructure interaction for this structure, which I thought a particularly interesting aspect of the design. Well, let's talk for a little bit in general terms just about arch behavior. It's just been from my experience, reviewing models of arches, that sort of thing, that oftentimes people will just assume that the boundary conditions for a fixed end arch should just be a fully fixed support at each end. As we saw in this project, though, the actual boundary conditions of an arch, whether it's founded on rock or on tall or more flexible piers, and how flexible the foundation may be, actually play a very large role in determining what the forces in an actual arch will be. Often the actual boundary conditions are significantly more flexible than the assumption of just a fully fixed support at each end, and that additional flexibility then leads to often significantly higher bending moments in an arch than might be computed if you assume the end conditions of an arch were fully fixed. Now, I think traditionally when people think of an arch, you think of an arch, or say arch action, structure acting like an arch, as a element that primarily takes force and axial compression, acting like an arch, and has relatively little bending. That condition, that sort of ideal arch behavior type of condition, comes closest to being met if you do have fully fixed supports at the base of an arch, have an arch that follows the line of thrust, where the dead load axial force coming in at each joint between a spandrel column and the arch then exactly adds in magnitude and direction to the resultant axial force in the arch below the joint. And for a arch supporting just discretely spaced spandrel columns, the line of thrust is a polygon, so it's not a smooth curve. So this arch shown down here has the same span length as the actual arch of the Fulton Road Bridge. This condition here of an arch that is full on fixed supports is a polygon between spandrel columns, and then doesn't have any kind of incremental construction sequence, would come the closest to satisfying these conditions of an ideal theoretical arch where the load is just primarily carried by axial compression and there is little bending moment. However, as I mentioned, this type of ideal arch action is decreased by if the arch, the actual profile of the arch deviates from the ideal line of thrust. If there are flexible piers and foundations, that then the end conditions are not fully fixed, they're flexible, and if there's some type of incremental construction sequence, all of these factors will result in the load being carried by a higher proportion of bending moment and a lower proportion of axial force. So to look at this issue a little further, we did just some general studies where we did model an arch. We considered this ideal theoretical arch for one span of the bridge that had these ideal fully fixed end conditions and an ideal profile following the line of thrust, loaded it with the actual dead load plus half span live load from an actual arch line that the bridge would experience, and then looked at the internal stresses, because arches are, in terms of bending, are most sensitive to asymmetrical loads. So an asymmetrical half span live load would tend to generate the largest bending moment. So then looking at the internal stresses, where here axial compressive stress, or just compressive stress, is negative, you see that for this ideal case, the stress inside the arch rib is almost completely compressive, in axial compression. So this theoretical case is acting as a theoretical arch one would think it would act, carrying the load and basically complete axial compression. Then when we looked at the actual case of our actual bridge, where we have arches that, for aesthetic reasons, are curved between spandrel columns rather than being a polygon, and rest on tall piers on somewhat flexible foundations that are founded on shale, there's quite a bit more tensile stress in this arch from the same loading as you'd have in that ideal case I showed before, where these spikes in our tensile stress here, you can see it gets up to, this is just a service load of positive, 1 KSI, located in many cases near the joints of the segments, is traditionally high, is significantly higher than what you get with this ideal case. So let's look at that. Let's look at the actual versus ideal case in terms of moments. So here's the moment diagram. There's a gray line for this ideal polygon case for the same span length and load as an arch line in the actual structure. Well, the dark black line is the moment diagram for the same loading on the an arch line of the actual bridge. You can see bending moments are significantly higher for an arch of the actual structure versus this ideal arch case up here. So ideal up here, actual down there, with significant negative moments near the ends of the arch. And I should add, these are fully fixed arches, no internal hinges, and then significant positive moments that reach their maximum where the spandrel columns frame in to the arch. And I don't want to get too into the meaning of this graph here, but suffice it to say, as part of our design, we did a sensitivity analysis to see how much introducing each, going from this theoretical case to the actual case of the arch had on changing bending moments. You can see that this purple line, dashed purple line, that would be from this ideal polygon case, and then we kept making the arch more and more flexible by making it closer and closer to the actual case, where we say instead of being polygonal, in red now it follows the parabolic curve. Instead of being fully fixed at its base, now it's on tall piers on the blue line. Then instead of having the tall piers be fixed at their bases, they're on the actual, they have the actual spring constants of the spread footings on shale, the green line. And then we incorporate moments based on the anticipated construction sequence, how it's sequentially erected rather than just all at once, and you get the total moment in the yellow line. So you can see that all of these, adding all of these parameters to the structural modeling of the bridge have quite a significant effect on bending moments. Like here in about the same location, we're at a moment of, I don't know, like a negative moment of about, like, what would you say, that's about negative 500 kip feet for the ideal case, and then we're at negative 4,000 kip feet for the actual case. So this just goes to show, if you're modeling and analyzing an arch, be rigorous and careful about how you do it. Don't just assume it's going to be fixed at its end unless it truly is really fixed at its end, because the boundary conditions for how an arch is modeled really have a tremendous effect on the output forces you'll get from your modeling of the arch. So given that we had these high bending moments and we're creating the arch out of precast segments, since the segments were precast, joined together, we thought it'd be appropriate to meet the concrete service limits prescribed in the AASHTO code. But for a completely fixed end arch, that's a little easier said than done. Because if you try to just post-tension the completed arch all at once, the restraint of the fixed ends, the fixed bases, will then induce a restraint moment, a secondary pre-stressing moment that will basically completely counteract any beneficial moment you could induce in the arch through pre-stressing. Now, our solution to this problem, however, was to pre-stress the arch, we'll post-tension the arch incrementally during the construction sequence to then lock in beneficial pre-stress moments before the arch became fully fixed. So here's a little run-through of the actual construction sequence and how the post-tensioning works that we ultimately designed. So begin by casting the thrust blocks, the end piers in place. Then we start by erecting the end precast segments on temporary towers. These segments are shipped from the precaster without any internal post-tensioning. They're robust enough for that to happen without them cracking. Then closure pores are poured between the end segments and the pier base, and two 19-strand post-tensioning tendons are then tensioned from the pier base through the end segment. And because at the time these tendons are tensioned, the arch is not yet a fully fixed arch from end to end. It's able to deform under the load of this post-tensioning, so we're able to lock in beneficial moment opposite in sense to the the dead load moment we're trying to counteract by post-tensioning the tendons before the arch becomes fully fixed and continuous. Then the crown segment arrives. It's been post-tensioned at the precasting yard from end to end, and since this post-tensioning is added before the crown segment is erected in the arch, beneficial moments from this post-tensioning are able to be induced in this arch segment because there's no restraint to its deformations under this post-tensioning load, as there would be if this post-tensioning was applied once the segment was part of a fully fixed continuous arch. So that post-tensioning for the crown segment is applied first. Then the crown segment's erected on the temporary towers. Duct connections are made for our continuity tendons, which I'll talk about in a second, and then closure pores are cast between the crown segment and the end segment. Next, once those closure pores have cured, we do stress 4 15-strand post-tensioning tendons end-to-end the arch bridge through the arch span for continuity. Because at this point the arch is fully fixed, all these tendons do is induce compressive axial force. This is useful to counteract bending moments in the cast-in-place closure pores where there are no other tendons, and to just pull the whole arch together. But since at this point the arch is continuous, no primary pre-stressing moments are induced in these continuity tendons, and they have a symmetrical layout. So with this post-tensioning in place, you saw before that for the actual arch we had stresses for service dead load plus a half span live load significantly above the maximum allowable tensile stress prescribed by AASHTO. But with the post-tensioning in place, stresses are all compressive, still quite a bit above the maximum allowable compressive stress. So our stresses are in a good place, so to speak, meeting these stress limits of AASHTO for a precast concrete structure. Now this, see this again during construction, but our post-tensioning crosses over and overlaps in the pier base. The ducts cross over. This was the most complex part of the structure to build, but it did, by having them cross over, it made the post-tensioning operations a little easier since there was plenty of room to access the post-tensioning tendons and to jack them without the jack running into any concrete portion of the bridge. So that's the post-tensioning design aspect of the arches. And another aspect of the arch design I found pretty interesting was thinking about what would be the appropriate effective length AASHTO K factor to use for an arch on tall piers, so that we could do moment magnification, slenderness analysis. Because the AASHTO code it specifies effective length K factors for fixed end arches, but as we saw from doing these parametric studies, an arch on tall piers is quite a bit more flexible than a fixed end arch, and AASHTO is silent on how to factor that additional flexibility into a moment magnification procedure. Well, we found our solution from reviewing the literature for cast-in-place concrete arch bridges in the past. The sort of arch bridge we were designing, a multi-span viaduct on tall piers, really not too many arch bridges were designed with this form after World War II. Most of that type of arch viaduct is before World War II, before when labor was cheaper and concrete was more expensive. So it's a form that is economical on materials but more time intensive to build. And our solution came from a book about elastic arch bridges written by one of the preeminent concrete arch bridge engineers of the 1920s and 1930s, Connie McCullough, who is well known for the many beautiful concrete arch bridges he designed on the coast of Oregon. His book, Elastic Arch Bridges from 1931, describes a procedure, a general method you can use for analyzing a multi-span arch bridge structure on tall elastic piers, where you can think of it, each arch is just a single arch span that has some extended arch length down to a fixed support, which results in the same flexibility as the actual arch on tall piers. So we did some modeling and used that same approach to find out what would the extended length of an arch be that a single span arch on fixed supports be that results in the same amount of deformation and flexibility as one actual arch span on tall piers under the same loadings. So we did that, determined what this extended arch rib length would be, arch on fixed supports to result in the same deformation, and then for our moment magnification, used that length with the same effective length K factors would be prescribed by AASHTO for a fixed arch on fixed supports. We did some comparisons with second-order geometric nonlinear analysis, and they looked real close. So we felt good about this method for our moment magnification. We're happy we had read back in the past to Connie McCullough's text on the subject, which has a lot of other really good stuff too. I'd recommend finding this book, Elastic Arch Bridges, if you can. And since this bridge is made out of precast segments, which are sequentially erected in post-tension, to get the final state of stresses in the arch rib and to get deformations, and for geometry control, we knew that we needed to include time-dependent creep, shrinkage, and post-tensioning loss effects in our modeling, which we did. And these deflections are calculated, long-term downward deflections of the four camber and superstructure support displacements, which I'll get into in just a second. And as part of our analysis, the structure was analyzed at each phase of the construction sequence, at opening day and after creep and shrinkage effects had dissipated at day 10,000. Now, I want to talk a little bit about the interaction between the arch rib and the superstructure. So I mentioned earlier, the superstructure is continuous from end to end of the bridge and rests on bearings on spandrel columns over the arch rib. Because both the arch and the superstructure are continuous, as opposed to, say, the superstructure being simply supported between spandrel columns, This means that live load distribution between the superstructure and the arch rib is proportional to the stiffness ratio between the two. It also means that for a continuous superstructure supporting an arch, the live load moments are actually higher than for identical superstructure spans on fully fixed, unmoving support. So it was important to incorporate these higher moments into our design. Now here's a maximum live load moment diagram for the superstructure of the arch, and you can see here, looking at the superstructure, that the moments get steadily bigger, these live load moments, as you get towards the center of the span. So your total live load moment is both a function of just the live load moment in the individual span of the continuous superstructure between the spandrel columns, and an overall moment that gets larger towards the center over the full arch span, and is largest than in the superstructure above the center of the arch span. So we can see that trend of the moments getting larger to center. In addition to these higher live load moments towards the center of each arch span in the superstructure that we needed to be concerned about, we also needed to be concerned about additional moments that are induced in this continuous superstructure through downward displacement, long-term downward displacements of the arches due to long-term creep and shrinkage. The light black line here just represents arch superstructure moments just due to the HS25 maximum truck load. Then the light black line, that would be for a superstructure with the same span lengths, but on fixed supports rather than the actual spandrel columns that are supported by a somewhat flexible arch. And the black line, the thick black line, represents the actual superstructure moments due to the maximum HS25 live load, and you can see, as we saw in the previous slide, that these moments get larger towards in the superstructure towards the center of each arch span, versus if the superstructure was on fixed, unyielding supports. Then we have additional moments due to, this is then the live load moment plus the light gray line is the live load moment plus moments due to the moments at day 10,000 due to long-term downward deflection of the arch due to creep and shrinkage. So you have a sort of sinking support problem here, which then induces additional moments in the superstructure due to those long-term downward displacements of the arch under creep and shrinkage, which then resulted in an even higher moment than you would have if, say, you didn't consider any of these effects and just analyzed the superstructure as being on fully fixed supports. So fully fixed supports, thin black line, versus live load plus creep and shrinkage induced moments in the superstructure from downward displacement of the arch in the gray line. So quite a significant difference here, and is something you need to consider in the design of the continuous superstructure on a concrete arch. So those are the highlights of the final design of the arch ribs. My role on this project was to participate in the final design of the arch ribs. Myself always enjoy talking about that, and to perform the final design, we modeled the bridge using MIDAS Civil software. This was one of our first projects using MIDAS Civil. We used a 2D model for arch and superstructure for dead loads, live load plus impact, creep, shrinkage, post-tensioning effects, and thermal effects. Our 2D model used over 200 construction stages, while we used a 3D model for wind load effects on the arches and superstructure, since that was more transverse 3D behavior. So in our 2D construction stage model included the post-tensioning tendons. Here's just one of many stages, step 38, where in this case post-tensioning tendons and plate. Post-tensioning tendons are shown by the purple line here. And as this was a time-dependent analysis, it also included every dead load that was in place at the time, plus creep, shrinkage, primary and secondary post-tensioning effects, and any losses of force in the post-tensioning. We had two separate 2D models of the arch ribs, of the 6 continuous span arch ribs. Since just due to the site conditions, there were differences in the heights of the arch end piers. So this, as we saw before, these differences in height of the end piers create different stiffnesses at the end of the arches, which then create a different behavior in the adjacent arch spans in terms of how much moment versus axial force there would be in each arch. So modeling two different arch spans with two different sets of 2D models captured those differences. So here we're just looking at one representative construction stage where here this end segment B has been hoisted and pinned to the pier base. Support conditions are shown here, not shown. There are also spring supports in here to represent the foundations, and the temporary supports are shown right there. We'll get into a little more detail about how to do this in just a second. Now, in terms of setting up a construction stage analysis in MIDAS, this webinar intended to be a tutorial that will tell you everything you need to do to just go right and do that, but I did want to hit some of the highlights of setting up that analysis. We did need to define a compressive strength curve for the concrete. We followed the CEB FIP 1990 code. We also, following CEB FIP 1990, we had to define the appropriate creep parameters in MIDAS, and then we used the time-dependent material link function to associate each of the concrete materials with the appropriate creep and compressive strength functions that we had defined previously. MIDAS does have wizards, that sort of thing that can be useful in modeling different structure types. For the unique geometry of our structure, we created the model by importing nodal coordinates into it that were determined in an Excel spreadsheet using just a parabolic equation for the arch. We then using the graphical tools, then manually connected these nodal coordinates to define the elements and input loads. So it was you can do this either by just importing the nodal coordinates directly into the nodes table or by using the MIDAS MCT text file. It's really straightforward. So even if you have a structure such as this one that doesn't fit one of the preset wizards, you can get the model going by just importing the nodes and connecting them with elements inside MIDAS real easily. Since the arches are post-tension, we had to define tendon paths and tendon profiles for each tendon. These coordinates, like the arch root tendons themselves, like the arch root node coordinates themselves, came out of Excel. Just imported them into the the tendon profile generators of MIDAS. You have to associate the elements in your model that the tendon goes through, so MIDAS can apply it correctly. MIDAS also has a useful function where once you have a tendon profile in place, you can then copy and translate the tendon profile, which is really useful for, say, a repetitive structure like this where you have 6 spans with the same tendon profile. So then you can just, once you get it right for one arch span, you can then, or whatever it is you're modeling, you can then just translate and copy it for the other spans, and this profile insertion point box right here is useful for that. I mentioned we were doing construction stage analysis. There's a construction stage generator box you'll find in MIDAS, and we'll talk about that in a little more detail in just a second as well. So let's look in a little more detail about how one sets up construction stages. Let's go back to here's construction step 38, which I showed earlier. There's nothing particularly significant about this construction stage. It's just, I think, a useful one to illustrate how setting up a construction stage works. Again, this is representative of the condition where precast segment B here at the end has just been hoisted and placed on temporary supports and then pinned with a temporary connection to the pier base at one end before the concrete closure core has been cast between the end segment and the pier base. So looking at the model in a little more detail, here we have our temporary support that's modeled analogous to these temporary support towers there. Here's segment B. We have a temporary pin connection to the pier base that's modeled with a beam end release in MIDAS shown by the green circle here. And we have an applied load due to the pedestal that the spandrel column sits on, but that is not included in the self-weight of the segment B. Although the tendons in this arch rib have not been tensioned yet, this profile shows the tendons that will be placed along the arch. So you can think of this at this point as a tendon duct. So looking at how this step 38 is set up in MIDAS. If we go back to our construction stage composer, go down to step 38, select that, and hit show, then the first we'll see this compose construction stage menu here, and there are 3 tabs that show you what's going on: the element, boundary, and the load tab. Starting with the element tab, we can see that here the element tab lets you activate or deactivate elements by element groups. So looking at the tree menu in MIDAS, you can form element groups of any combinations of elements you like. You can group them together and give them a name, and then once you have these element groups, you can activate and deactivate them within this compose construction stage menu. One key piece of information here is that you can see we've associated an age with these elements of 90 days. Since we're doing a time-dependent analysis with creep and shrinkage, it's really important. Creep is the long-term displacement of concrete under a sustained load. Shrinkage is the tendency of concrete to lose volume over time due to evaporation of the water that goes into the mix. And both of these effects, creep and shrinkage, will result in long-term deformations of concrete elements. Now, if these deformations are unrestrained, as in the case of a statically determinate structure, they don't result in any additional internal forces in the elements as taken as a whole. Since this is a fixed end arch, though, it's a highly indeterminate structure, and any deformations then due to creep and shrinkage get restrained by the fixed end structure and then induce moments due to creep and shrinkage. So we have to account for those, and since the magnitude of creep is highest initially, has that kind of decreasing logarithmic curve here, we're defining how old the segment is when it first sees sustained load. So the older it is, the less creep there will be due to these sustained loads, because most of the creep in concrete will happen when the concrete's very young. So we had a 90-day aging requirement for these segments, precast concrete segments, which is then reflected here in this 90-day age in our composed construction stage dialog. Moving on to the boundary tab, as this so here back in the element tab, we've activated the segment B at the end, shown by the highlighted elements here. Going on to the boundary tab, we've activated the appropriate boundaries that are activated in MIDAS at the time the segment is activated. This so-called span 5 construction boundary condition gets activated. That's the pin connection at its base through a beam end release, and also the span 5 temp support B gets activated. That's the temporary support located at the top end of segment B. These boundaries are boundary groups, like the elements, they're groups, but a different type of group, a boundary group that is defined whenever you define a boundary condition in MIDAS, such as a support or a beam end release or elastic link. At the time you do so, you have the option to associate the boundary condition with a boundary group, which then you can view in the tree menu under the works, that you can then view in the tree menu under the group tab, which is what we did here for all these boundary conditions. So you can, just like the element groups, you can activate and deactivate them at different points over the course of the construction stage. So here you can see we're activating this beam element release to have a temporary pin condition at the base of this arch segment, and then a temporary support at its top. The third tab of the construction stage composition tool is to add loads that are activated during the construction stage. Here we added all our dead loads over the course of our construction stage model. Here you can see just our applied dead load due to this little pedestal on top of the end segment B to support the spandrel column. Like the others, you group these, as you're applying load during the construction stage, all the applied loads should be grouped into appropriate load groups, which then you can view in the works tree. So here we can see we have an active load group of this, segment 5B spandrel cap, or spandrel pedestal self-weight. So, pretty easy to use. It's a real nice way of introducing construction stages. I find it, ever since this project, and then too, I found it very user-friendly. Moving on to our live load analysis, we used the lever world to come up with distribution factors for how much of the superstructure live load each arch rib sees. As prescribed by the client, we used an HS25 loading with the lever rule that enabled us to use a 2D analysis for live load, where we defined a line lane over the length of the superstructure, where we used the appropriate boundary conditions between the superstructure and the spandrel columns. Looking at, say, how we set up a moving load case to run on this line lane, here's just the HS20 truck. That's a preset vehicle in MIDAS. Since we're using an HS25 loading, we scaled that up, 1.25. And then the scale factor, manual scale factor, we typed in up here, 1.91. This is the distribution factor that we obtained using the lever rule. And now for wind loads, as I mentioned previously, since this creates transverse bending in the arch rib, spandrel columns, and spandrel caps, we used a 3D model to determine these wind loadings, but our approach here of 2D for dead loads and live loads, since those are primary vertical loads, and then 3D for wind loads, this was a pretty simplistic way to go. We thought it would have been a lot more complicated with a lot of more additional analysis and modeling time to build up that construction stage model in 3D. And since each arch end pier is, they're all self-supporting, there isn't a lot of interaction between the arches, so this we felt, and did some study with our 3D model here just to confirm, but the 2D model was a good way to go. So now that we had the bridge modeled in MIDAS, we used the output from the model in spreadsheets which we wrote to perform the ASHTO service limit state checks for the arch ribs. We did strength check of the arch rib for axial compression and bending using the forces output from MIDAS in conjunction with the PCA column program. Again, we used a spreadsheet for shear strength check of the arches, and then strut and tie analysis for the post-tension anchorage zone in the arch segments themselves and the pier bases. Just to see real quickly how you can get forces, output forces from MIDAS Civil during construction stages. If you look at the top left, this is for MIDAS 2015, you can see the dialog box where you specify what construction stage we're looking at. Here we have it on step 38. Once you've done that, then you can go to under the results tab and then results tables. If you bring up B results tables, you'll see this dialog box. You can specify the elements you want results for under structure group here. Specify the elements in the structure group you want to see. Then you can select which loads you want. So say in this example, we're looking at dead load, looking at tendon primary forces. These are the primary pre-stressing moments, just pre-stressing axial force times eccentricity from the centroid primary force. Also, MIDAS will, for indeterminate structures, compute secondary pre-stressing forces. These are forces due to restraint of deformations on the structure from the primary post-tensioning. Just restraint of deformations from the post-tensioning gives us tendon secondary forces. And then the creep and shrinkage forces you want are creep secondary and shrinkage secondary. You also have the summation option, which will give you everything. And then you can, over here, if you already have the model set to the construction stage you're looking at, you'll have the stage you're looking at automatically selected, step 38 in our example case here. And then here you can select whether you the part of the element you're looking for results. The ends are part I and J, and then you can look in the middle if you want to. Our element lengths were quite short, so we didn't need to, just need to look at parts I and J. And then once you hit OK, then up comes a results table listing, for each element, axial forces, shears, and moments that you can then just copy and paste the forces from this table into, say, an Excel spreadsheet or other standalone document you have to do your code checks. So that's covers design. Looks like we have little time left to talk about construction. This project was bid in 2006, which is, you may remember this was, we hadn't quite hit the housing bubble had not been burst yet, so this was a time when there were rapidly escalating bid prices, and we had really our pencils to try to come up with what a reasonable engineer's estimate would be. We'd chosen just a general structure type that we thought would be quite constructible for Ohio-based contractors, and we were rewarded with a load bid that came in under the engineer's estimate. The low bidder was Kikosing Construction Company, who was a pleasure to work with. The Ohio Department of Transportation provided oversight during the construction process. The bridge is ultimately owned by the Cuyahoga County engineer. The construction project began with demolition of the existing bridge. The superstructure of the original bridge was just removed manually, but then explosives were used to demolish the 6 arch spans. The arch pier thrust blocks, I mentioned those earlier, but we've done some integrated 3D CAD modeling to make sure that our design plans for this congested region were correct and didn't have any rebar conflicts. And although there was a bit of a learning curve associated with forming and placing these elements, ultimately the contractor became pretty fast at them, and it really wasn't too much of a hindrance project to have this somewhat complex region. The arch segments were precast and fabricated by Car Concrete in West Virginia. There were 72 segments in total of 2 unique shapes, each is approximately 60 feet long. You can see here, just to reduce their weight, we used internal styrofoam voids. So in some respects, they were, not a little more complex, but not too different than the sort of precast box beams that are commonly used for bridges in, say, Ohio and Pennsylvania. So it was nothing too new and different for local precasters and contractors. The arch segments were erected on temporary steel bents. Towers, we saw some of those a little earlier. The towers took some more sort of unique special forms to get over the railroad tracks without obstructing rail traffic, and to get over a historic bridge that the new and old bridge is crossover in the zoo. I mentioned that there were closure pores between the arch segments. They were 1 foot 6 inches in length. Some pretty congested rebar in there, and for the continuity tendons, duct connections need to be made between the continuity tendons in the closure pore. And as I mentioned, there were 4 of these per each arch line. The post-tensioning was either for the crown segment, the crown segment PT that was done before the crown segments were installed. For the end segment post-tensioning and the continuity tendons, those were all jacked from the base of the end piers. So the DSI's post-tensioning contractor, they were able to have large unobstructed work platforms to work from for the post-tensioning operations. The prestressed I-beam superstructure was a 35-span, is a 35-span continuous superstructure consisting of AASHTO Type 3 beams fabricated by Prestressed Services, and all these beams sit on either elastomeric or Teflon sliding bearings as they get farther from the fixed point at the center of the bridge, giving 630 total bearings. And the superstructure had some nice unique details too, such as this tubular steel arch-themed railing, shot painted with field touch-up, and so that's a real short version of construction. It was interesting. We had a fun time looking back at the Cleveland State University archives of how the original structure was open. There were a number of festivities. This was no doubt a bright spot during the Great Depression for the neighborhood residents. Here's a photo of a beer wagon float in the 1932 parade when the original bridge was finished. All the folks here look like they're having quite a good time. For the bridge opening in summer 2010 for the new structure, I think it's safe to say the new structure opening festivities were a little more restrained. It was a fun run in June before the bridge was open to the public, then official ribbon cutting in July, followed by a parade of classic cars. And here's photos of the original bridge design team. This was taken in 1931. Then during the opening day festivities, here's a portion of the new bridge design team. The center there, that's Jeff Broadwater. He's the project manager, doing a great job. Not shown, John Dietrich, now Baker's National Director for the Bridge and Highway Practice, was instrumental in the preliminary and final design of the bridge as well. Mike Bittner, Chris Cummings, Kevin Geis worked on the structure quite a bit as well. Soen did a lot of the environmental work that allowed the project to proceed. So in the intervening time between 1931, I think that this picture is reflective in general of our, changes for the best in the engineering profession. Although, I guess, white shirt and tie never goes out of style. So thanks a lot for attending. Hope you enjoyed. Hope you enjoyed the webinar. Just wanted to share. Rendering was accurate, and now I'd be happy to take questions. And I think Midas is going to take it back. But before they do it, just want to note how remember how I talked about how there's 4 closure pores per arch span. If you look here, you can't see where they are at all. So Picosing did they did a great job. The project, you can't see where these closure pores are. Also want to thank Greg Kronsting and the Ohio Department of Transportation did a great job with the construction oversight. And with that, I'll take any questions we have time to answer. I believe Midas is going to take back the screen and show the questions.
Yes, thank you, Daniel. Taking back the screen here, and we're going to address some of the questions that our attendees have submitted. And so the first question that we're going to address here, we'll try to get to as many as we can. You mentioned continuity post-tensioning would induce only axial force on the arch rib. Can you explain why there will be no induced moments?
Well, for 2 reasons. Probably the most basic is that the post-tensioning, the profile that we chose for continuity post-tensioning is symmetrical about each axis of the arch, so there's no net there's no net eccentricity for the continuity post-tensioning, so that induces no moment. Second reason is that if there was a net eccentricity, there might be some net moment that was induced, but what we were seeing in our studies is that the fixity of having a fixed end arch, that any primary post-tensioning moment, just the axial force P times eccentricity E, was almost completely counteracted by a secondary post-tensioning moment just due to the restraint of the arch at its ends. So any bending that, any beneficial deformation that the eccentric post-tensioning would induce in the arch was then counteracted by a restraint to this beneficial deformation from the fixed end of the arch, which is why we then were able to induce beneficial primary pre-stressing moments into the arch rib by that staged post-tensioning sequence I showed before the arch became fully fixed and continuous from end to end.
Thank you. And the second question we want to address is the Elastic Arch Bridges book is useful to understand the theory in general. I'm not sure why it was needed if a numerical solution can be gotten from MIDAS. Can you clarify, please?
Sure. The aspect of design, we used some tips from the Elastic Arch Bridge where we're incorporating slenderness effects or just through ASHO moment magnification, and as part of following those procedures, you need to, there's a KL term in there, you need to say what the effective length of the arch rib is for the purposes of these calculations, and that K factor, the effective length factor, tells you what factor to multiply the half span arc length of the arch by. Now those effective length factors, which then describes how truly flexible the arch rib is for the purposes of these slenderness effects. Now for an arch that's fully fixed at its base, ASHTO specifies what that K factor should be, but it doesn't specify what it should be for an arch on tall flexible piers, which was the case for our arch here. So what we got out of that 1930s text was the idea that you can figure out what that value should be by modeling a single span longer arch rib length and extended arch that's on fully fixed piers, which has the same flexibility as an actual shorter arch span on tall flexible piers. So once you found that actual longer extended arch span on fixed piers, we know what the effective length K factor for that extended arch, for what a fully fixed pier should be, so we can use the specified effective length K factor for a fully fixed pier in conjunction with a longer half arch half arch rib length from the extended arch in the KL over R equations for moment magnification.
Thank you, Daniel. And the third question is, what was the construction stage model used to account for actual durations, cure times, etc., to monitor conclusions determined during design?
We did do some updating. Like, we assumed that the construction stage would be construction would go from the end to end, but it actually proceeded in opposite direction from the and we assumed, but we compared our results to an independent analysis, time-dependent analysis performed by the construction engineer, Jansen and Spons, using their Bruco software, and we got very similar numbers in terms of what the long-term, what the deformations of the arches due to creep and shrinkage would be at different period times of the design, which made us feel good.
That's good. How was the torsion in arches captured in 2D models?
We did a number of studies using our 3D model to kind of calibrate how asymmetrical, torsion loads placed on the arch rib would induce torsion in the 2D arch rib. So we had so that gave us a method to then take a 2D force and then add determine what applied additional torsion would be just based on the axial force in the arch. So we did that by studying specific applied loads in the 3D model and then calibrating our 2D model to reflect those torsion effects. So our ultimate design for the shear stirrups and the arch was in fact a combined shear and torsion design where those stirrups and longitudinal mild steel were designed for the effects of combined shear and torsion.
All right, and I think we're just going to address some of these construction related questions and we'll wrap things up. But number 5, did the contractor propose a different construction stage?
Well, as I mentioned just a little earlier, they proposed to erect the bridge in an opposite direction from the direction we'd assumed for design, but our idea that the bridge would be erected on temporary towers ended up being the direction they went as well. So, although particularly of the railroad tracks, maybe the placement of the towers was the specific of the towers was a little different, and the direction was different. The overall method of how the bridge was erected was similar to what we assumed in our modeling.
And one of our viewers would like to know if there were any lessons that were learned from the construction.
Oh, I'm sure there were a number of them. I'll have to refresh my memory. I think probably just in some of the specification writing for concrete and time between allowable pours at the precaster. The design proceeded relatively smoothly. Probably the largest hiccup is there was some asbestos-based tile used in the original structure, which had not been was not for whatever reason shown on the design plans of the original structure from the 1930s. And when that was discovered, there was a slight delay in the project. So probably the largest lesson I learned in this, and the project team learned, was if you have an old structure, even if there's no, say, old concrete structure, even if there's no potentially hazardous material shown on the original design drawings, do some cores in different locations to look for it anyway.
Oh no, that's really good advice there, Daniel. And I think that we're gonna wrap things up as far as the Q&A. And I just want to thank you again, Daniel. It's it's been a pleasure working with you myself, and I think I can speak on behalf of MIDAS that it's really great collaborating with you, and so thank you again.
Okay, thanks again for inviting me. Hope everyone enjoyed the webinar.
All right, Daniel, thank you. All right, we're gonna wrap things up here, and just a few things that I'd like to just share. MIDAS Civil, again, is a complete integrated bridge solution with full 3D FVA capabilities, optimized for bridge engineering, but capable of handling general structures. MIDAS Civil can handle both superstructure and substructure, as well as steel and concrete bridges. Would like to let our attendees know that we did just release new features for MIDAS Civil. MIDAS Civil 2016 version 2.1 was released this past week, and we now have PSC composite girder bridge design check and load rating features. Our website is northamerica.midasuser.com. We are also on social media, so you can find us on Facebook as well as on LinkedIn. Next, in 2 weeks, we will have Michael Roberts from HDR out of Portland, Oregon, presenting on soil structure interaction and ultimate capacity assessment of a large-scale existing movable bridge caisson. And this is going to be a very good presentation that you won't want to miss out on. And lastly, if you have questions about today's webinar, future webinars, or perhaps you have a question about MIDAS Civil, especially about our latest release, please email us at midasoft@midasit.com. For PDH credits, no need to email us to request, unless you happen to be watching with the group, which in that case, please email us with the list of your attendees. We will be posting a review page as well as sending out a review email along with the PDH certificates. And so you'll be able to see some of the questions that didn't get answered today answered. And I want to say thank you again. This is James Lee with MIDAS.